today, we're going to take a gentle first step into the world of statistics. If you've ever felt that statistics is full of complicated formulas and strange terms, don't worry. You don't need to be a math major to master it. All you really need to remember today are 6 key connections that link everything together and turn you into a better evidence-based decision maker. Let's explore them one by one. Let's start with descriptive statistics. Sounds complicated, but it's actually very simple. It's just about how we organize and summarize data, like tidying up your desk before a big meeting. Here are 5 students' test scores: 70, 75, 80, 85, and 90. If we say the average score is 80, that's already descriptive statistics in action. We are using the mean average to describe the center of our data. But average alone don't tell the full story. Are the scores similar, or do they vary a lot? For example, Class A, 78, 79, 80, 81, 82, very consistent. Everyone is close to the average. Class B, 50, 70, 80, 90, 110, much more spread out. The average has the extremes. Actually, both classes have the same average, which is 80, but the variation feels very different. That spread is called the standard deviation. Think of it as the average distance between each data point and the mean. Remember mean and standard deviation. These two are the heart of descriptive statistics. They are the core DNA of any dataset and the foundation for everything that follows. Oh, here's a business question. If we launch a new app, what will the average user retention rate be for all customers? Can we analyze data for all 30 million people in the target market? Of course not. It would take forever and cost a fortune. That's why we use samples. Just a small portion of the whole. It's like looking at a few pieces of a 1,000-piece puzzle and guessing, oh, it's a landscape. We study a part to understand the whole. If we randomly measure 1,000 people and find an average height of 6 feet, we can use that to infer the national average. That's the beginning of inferential statistics. But here's the key. Which pieces of the puzzle do we pick? If you only survey your company's sales team about the new product, your average enthusiasm level will be way off. That's where probability comes in. Let's make probability simple. When you roll one die, the chance of getting any number from 1 to 6 is equal. Now, what about if you roll 2 dice and add them up? There's only one way to get a 2, 1 plus 1, but 6 ways to get a 7. When you plot the results, a very specific pattern appears, a mountain shape. That pattern is called a distribution. Think of a distribution as the unique fingerprint of your data. It shows with which outcomes are common and which are rare. Each little probability adds up, forming the smooth curve. The taller the curve, the more likely that outcome is. There are many types of distribution actually, but one of them is truly special. The normal distribution, we called it the bell curve. Why is it so important? Because so many things in real life follow this pattern. People's height, test score, even the performance of machines and factories. Most values are near the middle, the average, and the extremes are rare. Here are 2 key features to remember. First, it's bell-shaped and symmetrical around the mean. 2, the shape depends only on the mean, where the peak is, and the standard deviation, how wide the bell is. Now imagine your company runs 2 different marketing campaigns. They have different scores, means, and standard deviations. How do you compare them fairly? We can't compare the raw scores directly. That's why we need to standardize the scores. Think of the standardization as translating different currencies into one universal currency like the US dollar, so you can compare prices instantly. Yes, the goal is to convert any distribution into a standard normal distribution, one with a mean of 0 and a standard deviation of 1. The simple result of this process is the z-score. At its core, statistics is about testing claims using evidence, just like a trial in a courtroom. We start with 2 hypotheses. The null hypothesis, this is the default assumption, nothing happened. No change, no effect. For example, the defendant is innocent. The alternative hypothesis, this is what we're trying to prove. Something changed. The defendant is guilty. We usually use a 95% confidence level, meaning we allow a 5 margin for error, a small chance that our findings happened purely by luck. We then collect data. If our data falls outside the normal expected range, the outer 5% of the curve, it's highly unlikely due to chance. This is where the probability value p-value comes in. The p-value tells us if the null hypothesis nothing happened were actually true, what's the probability that we'd see a result this extreme by chance. A small p-value like 0.05 or less means the result is statistically significant. It's probably not just luck, so we reject the null hypothesis. A large p-value means it could easily be luck, so we fail to reject the null hypothesis. Let's test this with a real example and put all these steps together. A cafe runs a new buy one, get one free promotion. The owner wonders, did it really increase sales? Or was it just luck? We'll use statistics to find out. Just like in a courtroom, we set up two opposing claims. The null hypothesis. This is the baseline assumption. Nothing happened. The promotion had no effect, and the average sales should be the same as before. The alternative hypothesis. This is what we are trying to prove. Something changed. The promotion actually increased sales. Then we gather the data. Before promotion average sales, $704. After promotion for 30 days, average sales $770. Sales went up. But is this difference meaningful? Or did the owner just get a few lucky days? We perform a statistical test, which gives us p-value, probability value. Our test result gives us a p-value of 0.028 or 2.8%. Remember our rule? We allow a 5 margin for error, our confidence level. Since our probability 2.8% is less than the 5% margin, the sales increase is considered too rare to have happened by chance alone. What this p-value tells us is if the null hypothesis were true, the probability of seeing sales as high as $770 purely by chance is only 2.8%. That's very low probability, so we conclude it wasn't just luck. So based on these statistics, we reject the null hypothesis. The sales increase is statistically significant. The promotion worked. Let's review the 6 connections we built today. Descriptive statistics, sampling, favorability and distribution, normal distribution, standardization, and hypothesis testing. Statistics isn't about memorizing formulas. It's a powerful tool for making logical, evidence-based business decisions. Once you see how the pieces connect, it's much simpler than you think. See you next time for more insights into data and decision making. Thank you.